Picture this. Your CEO opens a dashboard and asks one simple question. What is the average age of our users? Sounds easy, right? Except you have 100 million users, and each user record has 50 columns. Name, email, address, billing info, sign-up date, shoe size, probably their blood type at this point. A normal database looks at this and goes, sure, let me just read everything. 10 minutes later, you have got your answer. But a columnar database? 2 seconds. Same data, same question, 300 times faster overall. And no, it is not magic. It is geometry. Let us start with why traditional databases choke on this. A row-oriented database, like MySQL, PostgreSQL, or Oracle, stores each record as one contiguous block on disk. Alice's name, then her age, then her email, then 47 other fields. Then Bob, then Carol. It is like a phone book, every person's details on one single line. Now, when you ask, what is the average age? The database has to read every single row. Here is the painful part. It cannot just pluck out the age. The age is physically wedged between the name and the email on disk. So reading Alice's age means dragging Alice's name, email, address, and 47 other columns into memory with it. For a 50-column table, roughly 98% of the bytes loaded are immediately thrown away. On our 100 million row table, at about 1 kilobyte per row, the database reads 100 gigabytes from disk. The actual ages? About 2 gigabytes. The other 98 gigabytes ride the bus from disk to memory and straight into the garbage. 98 gigabytes of pure waste. So here is the big idea. What if you stored data column by column instead of row by row? A column-oriented database takes the exact same table and rotates the layout 90 degrees. All 100 million names sit together in one file. All 100 million ages in another file. All emails in another file. Same data, same values, just a completely different layout on disk. Now when you ask for the average age, the database opens one file, the ages. It never touches names, emails, or any of the other 48 columns. Instead of reading 100 gigabytes, it reads about 2 gigabytes. The massive speedup comes from reading less data, not computing faster. The best optimization is always the work you never do. But it gets even better. Columns compress incredibly well. Think about it. A column of ages is all numbers. A column of country codes is the same few strings over and over. When every value shares the same type, the compressor can make assumptions a general-purpose algorithm never can. Let me show you the menu. First, run length encoding, or RLE. If you sort a column of ages and get 1,000 consecutive 22s, you do not store the number 1,000 times. You store 22 times 1,000. One value, one count. Next, dictionary encoding. A country column with US, UK, and India. Build a tiny lookup table, 0 for US, 1 for UK, 2 for India, and store just the tiny numeric codes. Way smaller. Then, bit packing. Ages from 0 to 127. They only need 7 bits each instead of 32 bits. Almost 80% savings right on the spot. And finally, delta encoding. Monotonically increasing timestamps. Store the differences instead of full numbers. They are tiny and compress beautifully. The real trick, engines stack these techniques together. Apache Parquet, the format behind modern data lakes, runs dictionary encoding, then RLE, then snappy or standard on top. The result is often 5 to 10 times smaller than traditional row storage. There is one more crucial trick, vectorized execution. Once you have got a contiguous array of ages in memory, instead of looping through one at a time, the engine loads a batch, typically 1,000 to 4,000 values, into a CPU register and processes them all at once. Modern CPUs support SIMD, single instruction, multiple data. One single instruction can add, compare, or filter 8 or 16 integers in a single clock cycle. One instruction, 16 results. Row stores can almost never use SIMD. Their values are scattered across records with different types jammed between them. But a column store hands the CPU a flat, packed array of identical types. Exactly what SIMD wants. This is why modern analytics engines like ClickHouse, DuckDB, and Snowflake are blisteringly fast. They all use vectorized execution to squeeze every drop of CPU power. So if columns are this good, why did we not just switch everything? Because there is a real trade-off. Writing is where column stores pay the price. Inserting a single new user into a row store is easy. Append one block to one file. Done. That is one write. Into a column store, you must append a value to every single one of 50 column files. That is 50 separate writes. And if one write fails, your columns disagree about how many rows exist. Not great. Updates are even worse. In a row store, find the row, overwrite in place. In a column store, find the offset in one file, rewrite carefully, and coordinate 49 other files. Most column stores batch updates into a delta store and merge later, adding latency and complexity. This is why both architectures exist. Row stores power OLTP, checkout flows, logins, and single record lookups where you need the whole row fast. Column stores power OLAP, dashboards, reports, and aggregations over millions of rows. Modern data systems run both layouts side by side. The idea is not new. Copeland and Koshafian first described column storage in 1985. MongoDB built a working engine in the 90s. But the true game changer was CStore, published in 2005 by Michael Stonebreaker at MIT. It proved that columns, combined with compression and late materialization, could outperform row stores by over 10 times. Stonebreaker commercialized it as Vertica. Amazon launched Redshift in 2012. Snowflake launched in 2014. Google BigQuery was columnar from day one. And Apache Parquet made it the default storage format for data lakes worldwide. Today, whenever you query large data, you are almost certainly reading columns, whether you know it or not. So, that CEO question: average age of 100 million users, row store, 100 gigabytes and a 10-minute wait. Column store, 2 gigabytes and 2 seconds. Same data, totally different layout. Sometimes the smartest optimization is just turning the table sideways. So which do you prefer, 10-minute rows or 2-second columns?